things, yeah. Yeah. Oops. Okay. Last but not least. Thank you again for coming.
Oh yeah, sure. I'm glad I could finally made it.
Yeah.
I had like no free time, so okay, January. Yeah, but no, actually I'm off because I'm NERSEC director in the spring. But usually I teach in the spring, but the Princeton classes don't start until the early February, late January. And usually I take winter breaks to be either in Germany or somewhere else, so I'm barely around. Yeah.
Okay, everybody here? Yeah. You survived last night? Yeah. How was the training? Thumbs up? Good. You ready for day 2? Yeah. Excellent. Okay, again, let us know if you have any concerns or remember tonight you're on your own for dinner. Yeah. We have lunch. Okay, so let's continue. Our next speaker is Leslie Schoop from Princeton in the chemistry department, correct?
Correct.
Correct. Leslie, and you have spoken here before, I believe.
Have I?
Yeah.
Oh no.
Yeah, you have. It was several years ago. Yeah.
Oh my god.
Anyway, maybe it was at the workshop, I forget. But anyways, Leslie's a great synthesis scientist, and she will tell us about the materials. Thank you.
Great, yeah, thank you, JP. Okay, so I put my today's talk a little bit under the theme of, okay, what my title said, what materials we're studying, in the sense that yesterday you got a great lesson on what it takes to grow a crystal, and maybe you've realized that this takes quite some effort. And so the message here is that you want to select a material that you want to grow and then study carefully, and not just go for a fishing expedition, grow as many crystals as you can, hoping you find something cool, as the labor that goes in there is kind of intensive. And so I want to talk a little bit about strategies of how we pick those materials. However, I put like a little bit of a detour and stuff in this talk because this is a school, so I hope I'm going to get to the main message in the end. If I run out of time, you can catch me in the coffee break and I'll tell you the secret there. Okay, I think I can keep this short. This is just some kind of motivation of why we want to study crystalline inorganic compounds, not only quantum materials in general, because they have a lot of cool energy and energy-related and quantum applications. But the question is, which materials actually do find its way up all the way to applications, and if you look into that, this amount of materials actually so far is pretty small. So I like to show this pyramid of materials. Oh, and I need to give a disclaimer right now, because the field is bad. I'm going to do a bad thing now too, and I'm going to use the term materials for crystalline inorganic compounds. If I would give this talk somewhere in the soft matter school, so they would ostracize me for me, rightfully so, right? But people do that in the literature all the time, and if I show papers, you will see the word materials when they actually mean crystalline inorganic compounds. But okay, so you have this pyramid where at the bottom you have all of these crystalline inorganic compounds. And then there's a subset of those materials where we know, I wrote here, we know the properties of, but actually it's correct, we know some properties of. So only a subset of these we have measured anything more than the crystal structure. And then there's even a smaller fraction of this materials where we discover new physics. So if you go to conferences in condensed matter physics, you will notice that the number of materials that are being studied is relatively small compared to the number of materials we know. And then the apex of this pyramid is the materials that actually find it into applications. This really is just a few handful of them. So how do we move up the pyramid? That is the big question, right? How do we smartly move up the pyramid? And first of all, what do we do with the base of the pyramid? How do we know how many materials are there? So we can first look what are the known materials that we have, and you might have heard about the materials project or the inorganic crystal structure database. Those are really cool resources where we find all known crystalline inorganic compounds tabulated. So the ICSC mostly lists experimentally known and verified compounds. So these compounds, people have measured the crystal structure of it, and so this data is pretty good, although, I mean, if the data is old, the refraction might have been not that good, and the crystal structure might not be fully accurate in this database, but still it's relatively reliable. And I put a screenshot there and says it now contains about 300,000 crystal structures. However, if you account for duplicates, many of these entries are there many times. Like people measured sodium chloride, for example, very often. So if you take this out, you have about 50,000 unique inorganic crystalline compounds that we know. And then there's the materials project, which also includes theoretically predicted compounds. So those ones you have to take with a grain of salt, and we go into this a bit more in detail in a second. But they list about 150,000 compounds. And they have some more properties compared to the ICSC that show the band structure also. So you can use this as your data set to start finding. 50,000 doesn't sound that much. It's a lot because we study the properties of pure, but it's not that much. It doesn't seem an impossible phase space to explore. And so therefore there's a good motivation, also a reason why you would want to find more crystalline organic compounds or materials beyond that. As, for example, some high-throughput searches for topological materials have already shown that we couldn't really find something that is better than bismuth selenide, which was one of the first, or bismuth telluride TIs known, right? So we already reached the limits in some of the properties, so it might be useful to extend the spaces of 50,000. And people have tried that using AI. So you might have seen this paper from Google that claimed to have found as many as 2.2 million new structures using AI. And I just want to be fair to the authors, they say 2.2 million stable materials, although the vast majorities of those are metastable. And there's about 480,000 or something materials that they claim are new and stable. And so I copy-pasted this from the abstract that the claim is that this represents an order of magnitude expansion to stable materials known to humanity. So now if we know these filters of like which materials are those that we're studying, and we have an order of magnitude more materials, that would be great. I'm going to get to how we select these materials before, but having a larger base, of course, enables us to get better materials, right? But I just want to point out that these claims, you always have to take with a grain of salt. So I actually downloaded all those files, these 400-something thousand zip files, and I just started clicking through this, and I'm just going to show you one of my favorite materials. I could do this forever, but I don't have that much time in the summer school. But here, this is one of the stable ones, not the metastable one that you find there. So this is a water molecule and 6 hydrogen molecules, which somehow I forced into a crystal. And I'm not really sure how this should maybe make up a stable material. So I'm a chemist. Any chemist who show this will know this is a gas, right? So it's not a crystal. And so I wasn't the only one looking at this. There's actually this really nice paper that I just want to highlight briefly from Tony Cheetham and Ram Cheshari, who looked for all these materials. And what I copy-pasted here from the abstract is this most important sentence where I said we examined the claims of this work here, unfortunately, finding scant evidence for compounds that fulfill the trifecta of novelty, credibility, and utility. So they looked in quite a bit of those. And I just wanted to say the main takeaway of this is there are many of these compounds that are new, and I'll show you a different paper of reasons of where this is coming from. But there are also compounds that could be new, but they're not surprising. So if you take a known crystal structure, and let's say it has sodium on one side, and then it is not known with potassium on that side, it wouldn't be very surprising to a chemist that the material with potassium also can be grown. Okay, and this basically puts this one wedge materials worth studying into prospect, because why should I make the potassium material just because it might be a new material if I don't have a reason to make it because it has a cool property, right? So why would I do and put all this effort in? And you saw yesterday how crystal growth works, right? And so it is, it's not really useful to have these materials, but we already kind of know from chemical evaluation that they must exist, right? Yeah, I wanted to briefly talk about this paper before I come actually to the how we're going to move up the pyramid discussion, because this paper came out at the same time as this Google DeepMind paper, and it kind of backed it up. And here in this paper, they claimed that they picked 58 target materials from that list, and they had a fully robotic and AI supported lab try to synthesize those so that it ran fully autonomously. And over 70 days of continuous operation, that lab, according to the abstract, which again copy-pasted here, realized 41 novel compounds out of its 58 targets. So that would be a success rate of over 70%. And so just to know how it works, so the robots, they came up with a synthesis recipe based on, or the AI came up with a synthesis recipe based on reading the literature. The robots put materials into mortar, they made the materials, they put it in a furnace, they took the samples out, regrind, put it in a furnace, and then took an X-ray spectrum, and then the AI tried to fit the X-ray spectrum and decide if the material was made or not. And it made a loop of this. And so if it really made, within 70 days, 70% of those target compound, that would be a big deal, and would also mean that this materials prediction papers is actually better than we thought. So, but in this time, me and my colleague Rob Palgrave of University of College London looked into this, and unfortunately we came to the conclusion that we found shortfalls in all the 43 synthetic products. So I had 41 before, but there's 2 others that they say they manually made later. So we looked at all of them and came to the conclusion that actually no new materials had been discovered in that work. And so I just want to give a little bit of a basic overview of how we came to this conclusion, and also to give you an understanding how to do critical reading of materials that claim synthesis. And this is not only relevant for autonomous or AI-driven synthesis, this is also relevant for any kind of synthetic paper when the analysis isn't done carefully. Claims are often made in the literature that don't hold up. So I just want to talk a little bit about synthesis. I mean, you made some, so I'm going to keep this short. You made some samples before. But I just want to say that there's a difference between making polycrystalline samples and single crystalline samples. So for polycrystalline samples, you can do the shake and bake method, how people call it, which is very common for making oxides, where you really just put your starting materials in a mortar, you grind them, and you fire them in an oven, and you do that repeatedly. Or you can, for intermetallic compounds, people use things like arc melting. And I just want to point out this shake and bake is what the robots used, so that might be the basis. So they didn't make any single crystals, they did the shake and bake methods, and they had powders. Of course, this is a school about quantum materials, so if you want to study quantum materials, you want to grow single crystals. You try that yesterday, so I'm not going to talk about how this works, but I want to point out that if you have a crystal, you can learn much more about these materials than if you have a powder in many cases. Sometimes you don't have the chance, it's hard to grow a crystal or impossible, so sometimes you have to work with powders. But if you have the possibility, it is usually worth shooting for a crystal. And so why is that? So one example is how you characterize this with diffraction. So if you do single crystal X-ray diffraction, you get a lot more data, which is a lot of this, or half of the data is lost when you do powder X-ray diffraction. You see a single crystal diffractogram on the left and a powder X-ray diffractogram on the right. And so because you have that fewer information, you have to make more assumptions in fitting your data, and you make more assumptions in solving a structure. And solving completely new structures from powder diffraction patterns can be really hard because of that lost information. It's not impossible, but often you need very high quality data. You need to go to a synchrotron. You might need additional data to support your claim, like from additional measurements to get a correct structure. Whereas if you have a single crystal, you don't run into these issues that much. So just some information of what all goes into fitting a powder pattern, because that's also relevant to what the robots did. So the AI, they tried to fit powder diffraction data to claim they make a new material. On the right, I'm showing powder X-ray diffraction data from a crystal structure that I solved during my PhD using synchrotron X-ray diffraction data, and it wasn't a very surprising crystal structure, but you see that I have a lot of counts. The peaks of intensity is very high, and then with that fit, I needed to fit, there's 2 different tick marks here, so I needed to fit 2 different phases to get accurate information about the structure. And the reason why this is so complicated is you see this here in this tree, there's a lot of information that goes into this powder pattern. Lots of this is dependent on your instrument parameters, where you measure on, also on your grain size of your sample. So it is not only the crystal structure information that is in your data, there's a lot of extra information that goes into your fit. And you might know the more parameters you have in the fit, the more you can overfit the data at some point. If you have too many, you fit an elephant into everything, right? So that you need to take into consideration when you want to solve the structure from a powder pattern. Then also I want to point out, if you want to solve a structure from the powder pattern, you should always combine it with chemical analysis. Right? Diffraction is based on scattering factors of elements, and sometimes they're not distinguished that super well. And so you want to have, in addition, some measurement like EDX, or which is non-destructive, or ICP-OES is something which can be destructive to get the chemical composition of your sample in addition. So you have that as input to fit your powder data, so that you actually are certain that those 2 things match, those 2 kind of measurements, and you have a better idea. Okay, I mean, there's a lot more things to say about it, but I'm going to cut it short. I just want to go back to the robots and tell you what went wrong. So again, the method they used here to grow these samples or make these samples is shake and bake. The powder samples, the characterization is powder X-ray diffraction and refinement only, and there wasn't any chemical analysis. So this is a table of these 43 compounds, and we identified 4 common errors. And you see here, that for almost all of them, if you pay attention, you see one of them has no errors. But for almost all of them, at least one of these errors is an effect. So one error 1 is that is a very poor fit to the data, so poor that you cannot say that this fit has any meaning. That's a pretty common error. Error 2 is that the CIF file that they use for the refinement is different to than what they inputted. So I don't know how they did not catch this. So they say this is this material based on materials project, and then you look into the refinement output file that was in the SI and is a different structure. That's not that common, but it happened. Yes?
For number 1, how do you define that?
I'll show you. I'll show you in a few slides. Good question. Error 3 is the predicted structure has ordered cations, but there's no evidence for that order. And a disordered version of the structure exists. I'll get through this. This might be a little bit complicated. And this is the most common error. About 2/3 of these materials have this. So I'm going to walk you through this. And then error 4 is that they did actually correctly identify the material, but it was already reported. So they must have missed this in the literature. And so you see one of these errors is present anywhere except this one compound right here. This compound was, by the way, reported while this paper was in review, so they were too slow to actually get there. But to be fair, I can give them that one compound that they correctly identified it. But it's easier. I'm going to show you in a second. It's easier to say something is correctly identified if you know that the materials exist, because then it's easier to fingerprint powder X-ray patterns. You have less burden of proof than if you claim a new material. So here I want to show you some examples of poor fits. So first of all, so this is the data which is in the SI of the paper. And first of all, powder diffraction patterns, they don't have enough intensity to do a meaningful fit to solve the structure. Okay, you cannot solve the structure from this data, but of course you could match it to known materials, but you see there's a lot of peaks unaccounted for. This could either be impurities or they could indicate a completely different structure. You see the intensities here don't match at all. So generally a rule of thumb is you want this red line, which is the difference between your fit and your data, to be as flat as possible. And this is not flat, okay? So this is not an acceptable fit. Like, even if I would do an undergrad lab course about powder X-ray refinement, I would fail every student who gives me that kind of fit. Yeah? Okay, so I want to show you the problem with this border. So here is a material that was predicted in Materials Project, which was one of the targets, manganese 3 nickel 04, and it has the space group PM free bar M, which is primitive cubic. And you see it's primitive because the manganese and the nickel, the manganese and the nickel here are ordered. They're distinct positions in this crystal structure. So if you go to the ICSD, manganese nickel 02, or manganese 2 nickel 204, if you want to put it in the same ratio as there, is reported. And here you have random occupation of manganese and nickel, 50-50 on each side. And in this case, you get a face-centered crystal structure. It's a rock-side structure. Okay? So that's a known structure. So now if I simulate powder X-ray diffraction of those, this is my simulated powder X-fraction of the primitive structure. This is of the face-centered structure, and you see they're very different. And now I compare it to the material that was made in this thing, and you can tell me which one they made. They're very obvious, right? So that's definitely not the primitive cubic structure, that's the face-centered cubic structure. So they made a material, if I assume that their stoichiometry is correct, although they didn't do chemical analysis, they probably made a version manganese 3 nickel 04, but in this face-centered structure. And so would that be a new material? Because on the ICSD I found only the 50-50 version. The answer is still no, because the solid solution between nickel oxide and manganese oxide, what this is very well studied and known. And of course, not any increment of substitution between the two ones will be listed in the ICSD, right? At some point we ask a question, what constitutes a new material, like 10% substitution, 1% substitution. So you cannot classify this as a new material. And here, more of those examples, and you also see that the powder X-ray diffraction isn't always an obvious indicator of this. So here, you see tin, antimony, lead, oxygen. Up here is the predicted structure, predicted new structure by Material Project, and down here is a known structure, known and listed in the ICSD. One is orthorhombic, the other one is cubic. If I simulate the powder diffraction patterns, they look almost identical. So just with powder X-ray diffraction, I'm not going to see a difference between those two structures. How am I going to prove that I made the orthorhombic one and not the cubic one, right? If I just do powder X-ray diffraction, I need a lot more information for that. Here's their data and their fit. You see the fit is poor. There's virtually no way in differentiating between the two materials. And here's our fit. So we just we cropped the data. We didn't get the original data, but we used the program to get the data from the files, from the images. And then we did our fit with adding the known materials and some impurity phases, and we get actually quite decent fit, a little bit better statistics than their fit with the known materials. So there's no reason to assume that this isn't a known compound out there. And so just because it's funny, I wanted to point out that, so this is just the comparison between the two fits closer up, so you can see. I think ours is a better fit, but even if they're identical, you always have to err on the side that you made something known, then you made something new in this sense, right? Okay, just because it's funny, this compound is actually known since forever. It's called Naples yellow. It's a pigment. It has been used by ancient Egyptians, later rediscovered in a Renaissance painting, and I guess now has been rediscovered by AI as a new material. But, yeah. Okay, one more example here is again, we have this predicted new compound predicted to be a perovskite structure with ordered cations. This is a known compound here with disordered smaller unit cells. X-ray patterns are pretty identical. Their fit is absolutely terrible. We made it fit with some impurity phases, which is a lot better using the known materials. So it's very, very obvious in no compound. So just to conclude this part is, it seems to work poorly so far to predict new materials using AI. But I guess the question then I was finding is maybe we can use AI for property prediction. Maybe materials prediction, or maybe it's possible in the future, and we just need to chat with people more and we can get there. But maybe the real answer is maybe we should think about structure to property relations, or how to predict the material we're studying using AI, using the basis of materials that we know it does exist or can exist by just making logical chemical substitutions. So can it find materials worth studying? And this talk shouldn't shit on AI too much because I'm going to show you that you can use it. But I'm going to show you one more bad example from Microsoft, and I'm going to move on to something real. So this is trying to find property prediction. So this is an archive paper from Microsoft, hasn't been published, thank God. But it was on the BBC and other news outlets. How Microsoft AI screened over 32 million candidates to find a better battery. I don't even know how they started with 32 million candidates because I'm sure we don't know that many materials. But okay, so they did here some kind of filter of 32 million things and came up with one new electrolyte for a battery. So it would be a cool property if it would be true. So I just wanted to look into that a little bit. So here's the filtering stuff, and here are 4 materials that they came up with, might be good materials, and then they tried to make them. And then they realized that all synthesis attempts result into this material, which is a well-known material. So that again shows how they probably had predicted materials that are unrealistic. The problem of disorder is also a problem here. So all these targets resulted in this material, and that is actually a well-known lithium-ion conductor. So that's known, it's studied, people know it's a good lithium-ion conductor. So then they thought, damn it, we found one materials already know, how do we save this paper? So they're like, oh, let's dope the lithium with some sodium. So they also made the chemical connection. And so then they measure the ionic conductivities here, and up here you see the ionic conductivity of the lithium version, which is known and is a decent ionic conductor. And here's the sodium version, was known to be a bad ionic conductor. And then surprise, surprise, in between, you get in between ionic conductivities, and somehow this is being sold as great batteries and materials that were newly discovered by AI. And I just want to give you some thought for a minute. How much energy it costs to run something like this, right? How many CPU hours was that to screen for 32 million compounds to come to this example that I would do fueled by a quarter cup of coffee? My brain could come up with that, yeah, and I'm sure it's yours too, okay? So we're not there yet, yeah? Okay, but these are bad examples. I just want to come up with some logic and maybe how we can use AI to then come to a bit more reasonable ideas. So, as I said, how do we look at materials that are worth growing, and how can we use chemical logic to do that? And so a little bit of like chemical logic, how we use chemical logic to find materials of good properties is basically what my group is working on. We don't use AI, but we collaborate with people who do. And so we do that in certain areas of near quantum materials. And so basically, we do that by trying to understand this triangle that I show here, which is the connection of crystal chemistry or crystal structure, electronic structure, and properties. And lots of fields do one part of this bar. They do structure to property relations, or electronic structure to properties, or crystal structure to properties. But I think you need to think about all 3 things at once to fully get a full picture of when a material is worth growing. And so I just want to show you some of these relations that are well known in the literature. For example, that's not my work, that has been established for some time. We can learn things from the electronic structure, like that if you have steep bands in an electronic structure, you're likely to have high mobility electrons. So if you look for a property with fast-moving electrons, maybe that's where you want to go for. If you have flat bands, you may have correlations, depending on the type of flat band. May lead to superconductivity. Well, it's debated, but if you want to look for any kind of correlations, maybe you want to look for flat bands in your band structure. And if you have what's called a band inversion, meaning the character of the bands switches or inverts, as I showed up here, that is a sign for topology. So if you look for topological materials, that might be a fingerprint you want to look for here. Okay, then what are the signs we can look for in crystal structures? Well, many of you might have learned, if you didn't learn that much about crystal structure, to look at it like I show here in sodium chloride, where this assumption is correct, that this is a way, where the crystal structure is a way to pack space with spheres, and how to fill space most efficiently by viewing your atoms or your ions as hard spheres. And this is correct for many, especially ionic compounds, But if you look at many other types of materials, especially when they're intermetallic, you see that this kind of thinking isn't always correct, because very often you see that there's some kind of bonds that look like covalent bonding between atoms in a crystal structure, and that can drive the crystal structure as well. And I'm going to argue that this type of covalent bonding between materials is actually very important to understand for properties. So this is the lessons one, it's like look for the bonds. So for this, I want to just give a very, very quick overview about the typical bonds in solids. So we have covalent bonds and ionic bonds, as I just showed, just so for you to remind you, covalent bonds, a typical covalently bonded solid is diamond. And here you have the electron density located between the atoms in the covalent bond. The typical ionic solid is gallium nitride or sodium chloride, what we have here, and here you have the electron density located at the anion, at the negative, more electronegative atom of the thing, so it's not between the atoms. But more interesting are maybe this kind of weird, less defined bonds, so they're metallic bonds. I actually don't like them. I don't really know how to characterize them. This is the chemical thing of this is just a sea of electrons around the elements. It's kind of delocalized in all directions of real space. So those bonds are kind of poorly defined and hard to quantify. But then we have these bonds that are actually like a lot, which are kind of metallic, kind of covalent. And these are what you have in graphene, for example, what you have in graphene, for example, they're called conjugated bonds. Or you can have them in some kind of solids when they're called hypervalent bonds. And these are bonds that are partially filled, so they're not localized between the atoms here, they're delocalized over the system, but this delocalization happens only in certain directions of your crystal. So it's not delocalized all over real space like a metallic solid. And I started liking those kind of delocalized bonds a lot because they can teach us a lot about properties. So for that, I want to make the chemical connection from bonds to bands, just so you have seen this before. I don't know if you know this amazing paper down here from Roald Hoffmann, which talks about how chemists can view band structures or understand band structures. And I just love to show this model about the one hypothetical chain of hydrogen atoms, which then form hydrogen molecules because it's bond formation in the band structure picture. And so basically, the idea is this is your basic Bloch function, and if you add just a linear chain of s orbitals, you will see that you get a fully bonded state where all your orbitals are in phase at gamma, and the fully anti-bonding states where all your orbitals are switching phase at the Brillouin boundary. And so you will get a band which moves up in energy and is half filled. But then, if you consider that you know already that a hydrogen chain doesn't exist and it forms a molecule, so you want to look at this problem with a two-atom basis so that you can form a hydrogen molecule. So here your unit cell is just one atom, so I cannot make a diatomic molecule here if my unit cell is only one atom. But if I double my unit cell to account for these two atoms, I will have to start at gamma with both the bonding and the anti-bonding atomic orbital of this unit. And so I will get the fully anti-bonding state at gamma and the fully bonding state also at gamma. And I move to these alternating phases here at the Brillouin zone boundary along the state. And if you look, these two states here are degenerate because all the atomic distances are the same. So I have always two white and two black spheres next to each other. But if I now change the atomic distances, mean I form the chemical bond, I will change the energy difference between those. Here I have two white ones closer together and then two black ones further apart. And here I have the two anti-bonding ones close together. So this will go up in energy, the other one will go down in energy. And so that's basically a mechanism of the Pius distortion, but it's also just a bond formation in chemistry. So in this case, these two things are equivalent. When I form the chemical bond, I distort my structure and I change the band structure. Why is this relevant? Because this kind of gives us an idea why delocalized bonding is so interesting. So we can use it to rationalize very intuitively how graphene works and why graphene has this cool band structure. So if you look at graphene, just very naively from a chemist's perspective, I would say, okay, it's just carbon. It has like 3 sp2 bonds, which I'm just going to ignore for now, and then it has a half-filled pz orbital. And then I have this in a honeycomb, but I ignore the honeycomb for now. So So if I draw like a chemistry band structure which doesn't exist in K-space, I have a filled sp2 band and then a half-filled PV band. And if I would sketch this out, ignoring my symmetry, I would somehow get a metallic half-filled band. Okay, that's not the band structure of graphene. This is like I ignored all the symmetry here. But it intuitively tells, I just want to say, a chemist intuitively will know that graphene must be metallic based on this very simple monatomic picture. We can understand it better and why it has actually this very famous band structure that graphene is famous for, including its Dirac cones. If you consider the symmetry very roughly, and you realize that it has 2 atoms per unit cell, and we learned from Roald Hoffmann and his hydrogen chains that if you have 2 atoms per unit cell, you just fold over the band structure. Oh, I forgot to mention this, sorry, that I should discuss the hydrogen chains, that going from here to here, this doubling, is the same as just folding this over. So I'm going to do the same trick now. Oops. I'm just going to say, okay, it has 2 atoms per unit cell, so I'm just going to fold over this band structure and then sketch it out to the next gamma point, and I will get a nice inverted band structure because here, this is my bonding and my anti-bonding part. Right down here's my bonding part of the band structure, here's my anti-bonding part. I sketch it over this switch character, and I have an inverted band structure. So that is step 1 of the hydrogen chain, which was doubling the unit cell and folding it. Step 2 of the hydrogen chain was forming chemical bonds and distorting this structure, and that doesn't happen in graphene. So we're stuck here, and that's why we get the Dirac cone from a chemical perspective. So why does it not happen? Well, people like to draw graphene like that, with perfectly delocalized electrons in these PZ orbitals. We like to talk, if in chemistry word, we talk about aromaticity, and it's a meaning that this doesn't distort. If we were to distort it in any way, let's say we put double bonds there, we would open a trivial gap. If we change electronegativities here, like in boron nitride, we open a trivial gap. If we buckle this and make graphene hydride out of this, we open a trivial gap. So as soon as we mess with this perfect delocalization of the electrons, we're killing the Dirac cone, and we're forming trivial covalent bonds that make our material, I don't want to say boring, but not graphene-like. So basically, to sum this up, is that you can say, very simplified model of graphene is that the delocalization is what drives the chemical band structure, and I have highlighted this in many of those papers before, but if I were to kill this delocalization, I wouldn't have the band structure of graphene. So that asks the natural next question, can I have delocalization like this in materials that aren't carbon-based? And I kind of answered these questions before by showing you these other kind of bondings that exist in solids, so you already know the answer that it's possible. But I just want to point out where these other types of bonding are coming from, because it's not that obvious. So you cannot have these conjugated bonding as in graphene. This is like solely limited to carbon chemistry. You cannot have that in any other element. Maybe over like very small molecular chains, but if you would make a fully conjugated 2D sheet, not a base of carbon, which has this conjugated bonding, before getting the Nobel Prize in Physics, you would win it in chemistry because it's deemed impossible. Okay. But you have this kind of interesting bonding in molecules, which is called hypo or hypervalent bonding, which exists, when you have too few or too many electrons in a system. And so I just want to give you a quick course about electron counting, so you understand why these are called hypo or hypervalent. So a fully valent system fills its shells from a molecule up here to the noble gas configuration. So any kind of stable molecule, you will usually count to 8, or if you have transition metals in it, enter to 18. And also for solids, that's true, like it's an ionic solid, you will count to 8 electrons, and you have an insulating electron solid. So in the case of the molecules I showed there, so one example we had was boron hydride. So if you look, boron here has 3 electrons, and then each hydrogen gives me 1. So if I add 3 plus 3, it's 6. 6 is not 8. That is bad. So it's hypovalent, too few valent electrons. And so this boron hydride is very unhappy because it has not 8 electrons. And what it does is it dimerizes to get rid of this and bridges these molecules through hydrogen atoms And then you have a delocalization of 2 electrons over free centers called a 2-electron free center bond. So the electrons are shared between boron, hydrogen, and boron here over this kind of delocalized bond. And so this is how pseudo gets 8 electrons. You can have the same structure with too many electrons. So if I would go back to the periodic table, you would find that phosphorus has 5 electrons. Each of the fluorine donates 1 to this molecule. So 5 plus 5 is 10. 10 is not 8. That's bad. It's too many electrons. In order to get rid of that, it will delocalize 4 of these electrons along this axial part of the molecule, so that at a given time, there's always only 8 electrons around the phosphorus. You cannot have more than 8 around it. Okay, so 4 of them are just jumping constantly in delocalization to make the phosphorus happy. So can we have that in solids? I already answered this before, but I want to show you how we actually know we can. So this is again a very beautiful paper from Roald Hoffmann, where he showed that in some solids you can have linear chains of hydrogen atoms or square nets of antimony. Linear chains of antimony or square nets of antimonies. And he writes fancy in this way: the simple Clem concept in those materials is violated, which is a fancy way of saying the counting to 8 is violated. And so then he says, in order to understand this, you have to classify those as hypervalent, and I just want to show you why. So here, in the case of the antimony square net, let me show you how the antimony square net works. So this doesn't exist in isolation. It exists in a solid where it is charged 1, so 1 time negative, so 6 electrons per antimony. Antimony is 5, and it gets 1 extra. And if I put 6 electrons on the square net, or on any kind of molecule, I would expect it to make 2 covalent bonds and have 2 lone pairs to be happy. I cannot really put 4 bonds and have 6 electrons, because then I would have 1 lone pair above and I would buckle the thing. It wouldn't be planar. So basically, I have a situation where I either have an undistorted square net, or I make this distorted zigzag chain situation where the bonding is satisfied. You can also understand why this bonding cannot be satisfied if you just look at the orbitals in this D4H symmetry of the square net, and you will see you have your S and PZ fully filled, and you will have PX and PY half filled. So that means I will have a bond, it's called a hypervalent bond, which has only 1 electron per bond instead of 2 electrons per bond in the system. These systems don't magnetize or anything. And so if I write down a tight binding model of these systems, and note that these square nets usually exist also in the site-centered cell, I will get a beautiful inverted band structure, which is kind of reminiscent of graphene. It doesn't have direct cones at the K point, but it forms a nodal line. So you see the resemblance maybe. So then if you look at real materials where you have these square nets, the question is, do all of them have these structures? Can we find the ones that are these band structures? Can you find the ones that have these band structures with the inversions, or can you just distinguish them from the ones that don't? So here are some of these example materials that are known. Structures in the ICSD where you have these square nets. You see, you usually have something else in between. And if you just look at the simplest crystal structure of that and the materials that are known in the ICSD, we find more than 500 isostructure compounds. So that was the work of my first postdoc, Sebastian, a while ago. And so here it's just color-coded which elements can sit on which side in the crystal structure. And now we could say, okay, whenever the green element, which makes up the square net, has 6 electrons, we could expect this hypervalent bonding. But actually to count the electrons is kind of hard, because we need to know the exact oxidation states on the other ones. And in intermetallic compounds, it's not always obvious to find the oxidation states. So we came up with a hypothesis and said, if this is really a chemical bond driving this, then the following must be true. It means the distance between these atoms within the square net must be smaller than the distance to the next atom above or below, because chemical bonding reduces distance between atoms. So if we take this hypothesis and then we make a plot where we plot these distances towards each other, we get plots that look like the following, where in the yellow, so here we plot the distance within the square net, to the next layer, and here we plot the distance within the square net. And that results that in the yellow area, we are in the region where we expect the chemical bond to be there. In the blue area, we are in the region where we do not expect the chemical bond to be there. And then we put all the materials that we find in the ICSD on this plot. And here, we did do electron counting when it was possible on the square net site. And whenever we count to 8 or 0, which means they are not hyper or hypovalent, the valency is happy, you see that these fall into the blue area of the plot. So we are kind of good in predicting bonds, because whenever they're not 8, 5, 6, or 7, we are here in the yellow area of the plot. Okay, and then we can look at band structures published for these materials in databases like topological quantum chemistry, and we find that these indeed are always insulators, and these indeed are very often topological semimetals. So we can see and work if it works with another crystal structure also. So we do it with this crystal structure. Here's the same kind of plot. This time I color-coded it a little bit different based on the band structure that they show based on simple DFT. So that we just look at the databases which use PBE-based DFT. And so whenever we colored it in green, it has a band structure which follows this tight binding square net model based on DFT. So we can expect these Dirac cones to be there. And you see the green dots are all in the yellow area of the plot as predicted. Whenever I color them red, they have a wide band gap. So no Dirac crossings. But most interesting are the ones that are colored blue, because those ones in PBE DFT in the databases, they're often metals, sometimes they're topological semi-metals. But you might have heard before that DFT, if you use simple functionals, tends to underestimate band gaps. So you want to be careful. So what we did is we typed this chemical formula into Google together with the word band gap for each of these blue materials. We found experimentally measured band gaps in all these materials. So that means that this thinking about bonding, the very simple approach, just measuring distances based on the crystal structure, gives us a more accurate qualitative prediction of a band structure than PBE-based DFT, which I feel like shows how powerful this method of thinking is. So with my last few minutes, I want to just loop back to the AI and see now if we can do something useful with this and can we teach that to AI. So we collaborated with Una, Kim at Cornell, and we gave her an expert curated data set. So we gave her a data set of these square net materials and distances and all the atomic factors that go in. And then we labeled it yes or no if it's a topological semimetal, not only based on DFT, but also on what we could find in the literature. So it was kind of a lot of effort to create this data set. Maybe AI can do that more efficiently from reading the papers, but we did that manually, right? We did like, if there was an ARPA study that was clearly yes or no, if there was a measured band gap, that also, if we didn't have any data, we used DFT. Sometimes if we thought the DFT was sketchy, we ran a better hybrid functional DFT calculation to confirm. And so that's how they created the data set. And then this is what how the data is being separated by the tolerance factor that we found, so our distance ratio. And you see it does separate the topological semimetals to trivials, but not as great as we originally thought. We worked with a smaller data set in our paper, so you see we have some wrong entries here. So we're trying to see if AI can recover this. It didn't tell AI about this ratio, but also if it can find more parameters to distinguish the topological semimetal from the trivial materials. And so it did. So here's a plot which shows at the bottom, it recovered our tolerance factor, our distance ratio. And then here it found a component which is the electronegativity of the element on the square net multiplied by the ionic radii of this element if it were in an FEC crystal structure. And so it found it can split the data quite well, although you see it's not perfectly separated in green and yellow if it uses these two components. What we did then is that we looked at those materials that are kind of messy here, a little bit more careful in our data set. And those were all materials where there wasn't any experimental input. And we ran more DFT. And we ran more hybrid DFT calculations to confirm the band structure. And we saw that some of these labels were placed incorrectly. And when we relabeled, we saw that it actually filtered super well with with these methods. So the AI could find parameters that can separate these materials, and it could teach us something about when we made a human error in labeling our data set. So that was pretty cool. I also like that it found our logic and it recovered it. We then gave it crystal structures where our logic doesn't work to see if it learned something. So we gave it materials in the rock side crystal structure that is cubic, and so now the distance ratio falls out because it's 1 everywhere, it's cubic. So our logic fails. We wouldn't know how to distinguish topological from non-topological materials with this. But we asked the algorithm from base what it has learned with the training set, which of these materials are topological, and it correctly predicts all the TIs that are known as rock salts with high probability to be topological. It also predicts some that are known to be trivial, so it doesn't get it completely right, but it didn't put any TI here and the low probability ratio. So I thought it was pretty neat that it did learn something about when a material is topological with that endpoint. So with this, I hope I gave you some positive note of that AI can do something, but I think it really depends on the input you give it, right? Data input is very important. And of course, what we did wasn't effortless. We put a lot of human thought into creating this data set, and then it came out with something meaningful, and maybe that's a way to move forward with this field. So I just want to summarize that I talked about delocalization in quantum materials, but the talk to it is limited to just granite materials, where this is important. Since then, my group has shown also for Kagome materials, and now we are moving on to pyroclo materials, that these kind of thinking of bonding really matters to predict cool materials and crystal structures. I don't have the time to go through that, but I just want to point out that this isn't a way of thinking limited to one class of materials. So this, I want to thank my group, the funding, all the collaborators, and thank you so much for your attention.
Thank you very much. There's lots of time for questions. Yeah, Bruce.
So thank you very much. Very nice talk. And so the AI studies that you showed at the beginning, which clearly were flawed, it seems that correcting at least part of it would be pretty easy, because you simply have to build in an algorithm for a little bit of attention to detail as to what's a good fit and what isn't. Is that not right?
Well, I mean, I guess one big problem is this problem with disorder that I showed you in predicting new materials. I don't really know how to fix it that trivial, because when you run a DFT calculation, you will always you cannot model a disordered material. You will have to create one of these supercells for DFT, right? So therefore, it's not surprising that many of these new predicted materials, if DFT was a basis, are ordered supercells. I guess maybe you need to put that in an additional step, checking does a smaller disordered version of this exist. There's actually this math guy somewhere in the UK, I forgot which university, who contacted me. It's a mathematician, and he wrote some kind of algorithm based on just finding positions in a crystal, just removing all the symmetries, just looking at atomic position and matching this, and then finding huge amount of overlaps in this genome database. And maybe that's a way to get out of this problem with the disordered versus ordered structures, that you realize that these are actually the same materials because the order doesn't exist. But it's like with DFT, it's a hard thing to get around. And then, of course, it's never impossible that these ordered materials do exist, but proving that is experimentally challenging. So for that, you have to take best would be single crystal. You have to take a definitely synchrotron X-ray. For oxides, that would be neutron diffraction. And then maybe you might see enough differences to say this is a
But the good fit and bad fit part, independent of I mean, that sounds like it's fixable.
Yes. So there are actually quite a few studies trying to automate X-ray fitting for using AI, and there are some better ones and then some poorer ones. But I haven't seen one, at least about a year ago when I looked into this carefully, which was truly convincing that it's possible yet, but I wouldn't rule out that it will be possible in the future, yeah.
It's pretty surprising. I mean, it's not like they were suggesting 1,000 new compounds. It was 40 compounds.
Mm-hmm. Yeah.
Does one wonder why didn't, do they purposely not check these 40 patterns and say,
but okay.
Is that not obvious?
I mean, this is now politically dicey, but what I might say to this is that I'm also I'm disappointed by this group, because this is not only a theory group. They have an experimental section, and they do actually very good work, and they would know how to do that. So I don't know why these two parts of the group didn't communicate, because that should have been caught. Yeah.
So, student question, and then Nick. Yeah.
So that when we are doing kind of the XRD measurement, so if we have basically like same structure for the material, is there any way that we can differentiate?
So if the simulated powder diffraction patterns is very similar, it is extremely hard. So you might see very small differences in the intensity in the simulated color diffractions patterns. Then you could maybe get some information by going to a synchrotron and put it in a very high bright beam and get a lot of information. But even that might not be enough. What you can then do is, for example, neutron diffraction, where you have different scattering factors and you might have different simulated patterns between those materials. And then with the neutron in addition, you might be able to say which of those structures is more likely. Otherwise, if you can't tell, the rule is to err on the side of what is known, right? You need to prove that is the unknown thing. The burden of proof is with you.
Yeah, so a couple slides before this, you had some number correlation that your search found, essentially, or that your AI found. And it involved the ionic radius. Can you talk a little bit? What does that mean to you?
Yeah, this is a yeah. That's a good point. So this is actually an element-specific parameter. So you can calculate. So this is one number for each element. So you can calculate that, and it will show you that it has the region here which is good, right? Which is between two extremes, like not too large, not too big. Will be highlighting all main group elements, which makes a lot of sense because we were talking about bonding. And these type of covalent bonds are more typically made by main group elements. So that's what it's
because it's a pretty narrow range of numbers.
Yeah. So there in our paper, we have a figure with the number on the printed on the periodic table, and you see exactly the elements written here.
Can I ask you a question of the students?
Yeah.
So how many students have used ICSD? How many have never used ICSD? Like half and half.
Or Pearson's.
Or okay, sorry.
Any kind of database.
Yeah, let's modify.
Straight.
Sorry, I just can't.
No, it's fine. Yeah.
Or it's a modified question to say ICSD or Pearson or some crystallographic database. So, okay, so if you've used a crystallographic database, raise your hand. If you haven't used any crystallographic database, wow, okay, good.
Go Pearson's. No.
Pearson's is much more refreshing than that.
Oh, really? I guess I'm.
Leslie, why ICSD then and not Pearson?
Because we have a subscription at Princeton, so I'm like biased. I don't actually know if you have Pearson's. Yeah.
What, Pearson's? It has more compounds. Yeah.
So, so the lesson we learned from this lecture is that currently AI is not super good at predicting materials or even material properties.
Let's say yet.
And is that because the AI relies a lot on these databases and first currently AI is not able to get or if we train AI with more chemical information or this chemical analysis information
AI,
eventually.
Very good point. So this current tries haven't considered any typical chemical rules. I didn't show all the crazy materials in the Google paper. There's also things like silver fluorine 38, where you have fluorine molecules and fluorine trimers somehow trying to be forced in a crystal. So if you would tell AI some basic chemistry, right, oxidation states that are possible, kind of points, and I think there's a lot of room for improvement. Yeah, I don't want to say that it will never be possible. It's just right now it's not working.
But you think in general, if you enforce more rules into the AI, I mean, you didn't talk about let's compare the AI of this kind of search to image recognition or photos or graphics. I mean, there you have billions of data sets, data entries, and here you have 40,000.
Mm-hmm.
You not think that that's a serious
That could be, yeah.
So you use this kind of search?
That is a fair point. I'm not a computer scientist, so I can't really speak to that so much. Of course, it makes sense to me. However, what I will say is that the data set that we used with UNA was even smaller. And when you put in chemical logic and restriction, you can make it not do stupid things. So I think it's a combination of that, and I think it's a little bit, God, it's going to be online, but I'm going to talk about it. But I think there's a little bit of arrogance in the AI community that they don't need to learn the basic foundations of what we have studied for so many, like for decades in humanity, and they can just get it from raw data. And so far, at least in our field, they've shown they can't. Maybe they can improve the algorithms, as I'm not a computer scientist, but so far I think it would be to their benefit to talk to us more to see what simple parameters to include to make the predictions more accurate. Yeah.
And I think part of the hope is that AI can reveal new correlations or new information that we don't know, right?
Right, but I
For that,
think
you need a huge data set.
that too. But I think also if you put some constraints in, then AI can come up with new things, within those constraints, and you can slowly start lifting them. I think it's just not really useful to start with 0 constraints, because then you come out with garbage, as you saw.
Okay, final question? Yeah.
So I was curious, like in this your AI model you use for this particular study, what sort of like chemical analysis things?
So the data set you put.
You discussed about the bonding analysis. Was that also put?
No, the bonding analysis was not put in there. The AI did recover this, but we made sure that the data set is correct based on chemical logic, right? So sure, it's based correct on data. Like if there was data, this is a topological semi-manual, it's clearly not, then that is great. But we couldn't find 1,000 papers of materials being studied. So we used DFT and we made assumptions. Sometimes there wasn't even a DFT calculation, so we made a chemical informed decision. We were like, okay, this must be an insulator from just chemical intuition. And so this is how we created that data set. Yeah.
Okay, we better move on. So thank you. Is Linda here? Oh, yeah.